Right now, 78 meters below the surface of the East China Sea, two machines the size of apartment buildings are eating their way toward each other through solid rock. They have been digging for months. One started from the mainland side, the other started from an island. They are grinding through granite, clay, and sand in complete darkness, under water pressure strong enough to crush a car, guided by satellites orbiting 200 kilometers above their heads. When they meet somewhere in the middle, deep under the ocean floor, engineers will celebrate. And then they will do something that sounds insane. They will take the machines apart from the inside, remove every component they can carry, and leave the rest down there, forever. The outer shells of these 4,000-ton machines will be sealed into the tunnel walls. They will never be brought back to the surface. They will never be used again. They will sit under the ocean for 100 years, holding back the weight of the sea, becoming a permanent part of the structure they built. Two machines sent down to do a job they cannot come back from. That is not a metaphor. That is the engineering plan. If you enjoy videos about construction and engineering that pushes the limits of what humans can build, hit like and subscribe so you never miss one. This story involves machines that eat rock, satellites in space, and a meeting point so precise it would make a brain surgeon nervous. To understand why China is building a high-speed rail tunnel under the ocean, you need to understand what life is like on the other side of the water. Zhoushan is a cluster of over 1,000 islands sitting off the eastern coast of China, near the city of Ningbo. If you have never heard of it, you are not alone. Most people outside China have no idea it exists, but the people who live there know exactly what makes it special and exactly what makes it frustrating. The islands are beautiful, rocky coastlines, fishing villages that have operated for centuries, some of the freshest seafood markets in all of China. The area is also home to one of the biggest offshore petrochemical bases in the country, processing crude oil that arrives by tanker from the Middle East and Africa. Hundreds of thousands of people live and work on these islands. Millions more visit every year for the beaches, the temples, and the food. The problem has always been the same. Getting there is miserable. For most of Zhoushan's history, the only way to reach the islands was by ferry. If the weather was good, the crossing took about an hour. If the weather was bad, and on the East China Sea the weather is bad often, the ferries stopped running entirely. People got stuck, cargo got delayed, businesses lost money. Hospital patients who needed treatment on the mainland had to wait for the waves to calm down. In the 2000s, China built a series of bridges connecting some of the larger islands to the mainland. That helped, but it did not solve the problem. The bridges carry cars and trucks, not trains. Traffic jams during holidays turned a 90-minute drive into a 4 or 5 hour crawl, and the bridges could not reach the outermost islands because the water between them was too deep, the shipping lanes too busy, and the storms too frequent for conventional bridge construction. China needed a way to get high-speed trains across the water. Not cars, not trucks. Trains moving at 250 kilometers per hour, carrying thousands of passengers a day, running on schedule regardless of weather. And the only way to do that across a busy shipping lane was to go under it. A bridge would block the massive cargo ships that pass through this stretch of water constantly. These ships are so tall that any bridge crossing would have to be built impossibly high to let them underneath. And a bridge at that height, exposed to the typhoons that hit the East China coast every year, would be an engineering nightmare and a safety risk. A tunnel solves everything. It goes under the ships, under the waves, under the storms. Nothing on the surface can touch it. But a tunnel under the ocean is not like a tunnel through a mountain. A mountain is solid rock. It is stable, it is predictable. An ocean floor is a mess. Layers of granite mixed with clay, mixed with sand, mixed with silt. All of it saturated with salt water under crushing pressure. The ground changes composition every few hundred meters. What works for digging through granite does not work for clay. What works for clay will fail catastrophically in sand. And if water breaks through at any point during construction, people die. This is the kind of project that most countries would study for a decade before even starting. China started digging. The tunnel is called the Jintang Undersea Tunnel. It stretches 16 kilometers from the mainland near Ningbo to the island of Jintang, the first major island in the Zhoushan chain. More than 11 of those kilometers run directly beneath the seabed. The deepest point sits 78 meters below the ocean surface. To put that in physical terms, if you stacked a 25-story building on the ocean floor, the water would still cover the roof. That is how deep these machines are working. The machines themselves deserve their own chapter in the history of engineering. But since this is not a textbook, let me just tell you what it feels like to stand next to one. The first machine is named Dingkai. The second is named Yongzhou. Each one is approximately 150 meters long. That is half the length of the Eiffel Tower, laid on its side and shoved into a hole in the ground. The cutter head, the spinning disc at the front that actually does the digging, is nearly 15 meters in diameter. Imagine a circular saw the size of a 5-story building, covered in hardened steel teeth and carbide cutters, spinning with enough torque to grind solid granite into gravel. Each machine weighs roughly 4,000 tons. That is the same as about 8 fully loaded Boeing 747 aircraft. These machines do not just dig, they build the tunnel behind them as they move forward. As the cutter head grinds through rock and soil, the excavated material is carried backward on conveyor belts and removed through the finished section of the tunnel. At the same time, automated systems inside the machine lift precast concrete ring segments into position and lock them together to form the tunnel walls. Each ring weighs several tons. They are manufactured in a factory on the surface, transported down into the tunnel on rail cars, and installed by hydraulic arms inside the machine. The tunnel is literally being constructed in real time, a few meters behind the cutting face, while the machine advances. Then the machine injects pressurized grout into the gap between the concrete rings and the surrounding rock to seal everything watertight. All of this happens simultaneously, continuously, around the clock, with crews working in shifts to keep the machine fed with segments, power, and ventilation. Now here is where the challenge becomes genuinely terrifying. The ground along the tunnel route is not consistent. Over the 11-kilometer undersea stretch, the machines encounter 28 separate geological transitions. 28 times, the ground changes from one type of material to another. Hard granite gives way to soft clay. Clay gives way to sandy silt. Sandy silt gives way to something else entirely. Each transition requires the operators to adjust the boring speed, the face pressure, and the cutting technique in real time. If they push too hard into soft ground, the tunnel face can collapse, allowing water to flood in. If they push too slowly through hard rock, the cutter teeth overheat and the machine can jam. Getting stuck 4,000 tons of machine, 78 meters under the ocean, with no way to reverse, is the kind of scenario that keeps tunnel engineers awake at night. There is a specific geological formation along the route that engineers flagged as the most dangerous section, a zone where the ground transitions from hard-weathered granite directly into water-saturated sandy silt within the space of a few meters. In normal tunnel construction on land, this kind of transition is managed by slowing down and reinforcing the face before proceeding. Under the ocean, at 78 meters of depth, with the full weight of the sea pressing against every square centimeter of the tunnel walls, the margin for error shrinks to almost nothing. One miscalculation in face pressure during that transition, and the sand liquefies. The water rushes in, and the machine floods. That is not a hypothetical scenario. It has happened on other tunnel projects around the world. The difference here is that you cannot evacuate workers quickly from a machine that is 6 kilometers into a hole under the ocean. The operators inside the control room monitor dozens of sensors simultaneously. Ground pressure sensors, water inflow meters, torque readings on the cutter head, temperature gauges on the bearings, vibration monitors on the drive motors. Each reading tells them something about what the machine is about to encounter. A sudden drop in torque might mean the rock ahead is softer than expected. A rise in water inflow might mean there is a fissure in the rock that connects to the sea above. Reading these signals correctly and adjusting the machine's behavior in real time is what separates a successful bore from a catastrophe. Chinese engineers modified both machines specifically for this project. They added water injection systems to the cutter heads to handle sticky clay that could clog the blades. They reinforced every seal and gasket to withstand the water pressure at maximum depth. They upgraded the drive systems to run continuously for months without major maintenance. Because if a machine breaks down under the ocean, fixing it is not a matter of calling a mechanic. It is a full-scale engineering operation that can delay the project by weeks. But the machines and the geology are not even the hardest part. The hardest part is making sure these two monsters actually find each other. Dingkai started digging from the Zhoushan side, heading toward the mainland. It has to bore over 6,000 meters. Yongzhou started from the Ningbo side, heading toward the island. It has to cover nearly 5,000 meters. Somewhere in the middle, Deep under the seabed, in complete darkness, surrounded by rock and pressurized water, these two machines are supposed to meet. Not roughly, not approximately. They have to align with each other precisely enough that the tunnel forms one continuous tube. If they miss by even a few meters, the entire project fails. You would have two separate holes under the ocean that go nowhere. Billions of dollars and years of work wasted on the most expensive mistake in engineering history. So how do you guide a 4,000-ton machine through 11 kilometers of rock in the dark and hit a target the size of a room? You use satellites. Specifically, China deployed 6 Beidou navigation satellites for this project. Beidou is China's own global positioning system, the same one we talked about in a previous video that is now more accurate than America's GPS. Normal satellite positioning is accurate to within a few meters. That is fine for driving directions. It is completely useless for connecting two tunnel boring machines under the ocean. So the engineers linked the Beidou satellites directly to the auto-navigation systems built into both machines. These systems track each machine's position in 3 dimensions, latitude, longitude, and depth, and compare it to the planned route hundreds of times per second. When the machine drifts even a fraction off course, the system sends corrections to the steering mechanisms, adjusting the angle of the cutter head in real time. The machine corrects its own course as it digs. It is like a self-driving car, except it weighs 4,000 tons and is boring through granite under the ocean. When Dingai and Yangzhou finally met beneath the seabed, the alignment error between them was less than 2 centimeters. 2 centimeters over 11 kilometers. That is the equivalent of threading a needle from one end of a football field to the other. The precision is almost impossible to believe until you realize that without it, the tunnel simply would not work. And then came the part that nobody talks about. The machines are done, the tunnel is bored, everybody celebrates. But now, there is a problem. These 250-ton machines are stuck. They cannot keep digging forward because there is no forward. They just met the other machine. They cannot back up because the tunnel they built is full of concrete rings, rail cars, equipment, and workers. And they absolutely cannot be lifted out because they are 78 meters below the ocean, encased in rock, and weigh 4,000 tons each. So what do you do with a machine that has completed its mission but has no way out? You take it apart from the inside. Engineers call the process shedding the shell. Workers climb inside the machine and begin disassembling it piece by piece. The drive motors come out, the hydraulic systems come out. The cutter head, which alone weighs hundreds of tons, is cut into sections and hauled back through the tunnel on rail cars. Every component that is expensive or reusable is stripped out and saved for the next project. The work takes weeks. It is meticulous, difficult, and done in a space that was designed for a machine, not for people to work in comfortably. When everything that can be removed has been removed, the outer steel shell of the machine stays. It remains embedded in the ground, sealed into the tunnel structure, becoming a permanent part of the wall. The shell that once housed one of the most advanced boring machines ever built becomes reinforcement against the pressure of the ocean above. These machines were designed to do one job and then cease to exist as machines. They were built to become infrastructure. Every component was planned with this end in mind. The shell thickness, the metallurgy, the corrosion resistance, all of it was specified not just for the boring phase, but for the 100 years of service that would follow. The machine does not just build the tunnel, it becomes the tunnel. There is something about that idea that goes beyond engineering. A 4,000-ton machine that spends months grinding through rock in the dark, guided by satellites, correcting its own course centimeter by centimeter, and when it finally finishes, it is sealed inside its own creation and left there forever. It never comes back up. It never sees daylight again. It did exactly what it was built to do, and then it became part of the thing it made. The Jintang Tunnel is on track to be fully bored through by the end of 2026. After breakthrough, another year of finishing work follows. Track laying, electrical systems, ventilation, lighting, safety equipment, and all the systems that turn a hole in the ground into a functioning high-speed rail line. When it opens in 2028, the trip from Ningbo to Zhoushan will take 30 minutes instead of over an hour. Passengers will ride at 250 kilometers per hour in air-conditioned comfort, while the ocean sits silently above their heads. But this tunnel is not just about connecting two cities. Engineers who have studied the project believe it is a rehearsal for something far more ambitious. The Taiwan Strait, the body of water separating mainland China from Taiwan, is about 130 kilometers wide at its narrowest point. That is roughly 8 times longer than the Jintang Tunnel. The water is deeper, the currents are stronger, and the geological conditions are more complex. A tunnel across the Taiwan Strait would be the most ambitious construction project in human history. Whether that tunnel ever gets built depends on politics and economics that go far beyond engineering. But from a purely technical standpoint, the Jintang Tunnel just proved that every piece of the puzzle works. The machines can bore through mixed geology under the ocean. The satellite guidance can achieve centimeter-level precision. The shell shedding technique can handle the machines after breakthrough. Every technology needed for a longer, deeper, more complex undersea tunnel has now been tested and validated under real conditions. China has already built more than 45,000 kilometers of high-speed rail, more than every other country in the world combined. They have mastered bridges, viaducts, mountain tunnels, and now ocean tunnels. Each project pushes the boundary of what is considered possible, and then the next project pushes it further. 2 machines are under the East China Sea right now. When they finish, they will be taken apart, stripped of their insides, and left in the dark under millions of tons of water and rock. They will hold the tunnel walls in place for 100 years. Nobody will ever see them again. And somewhere above them, passengers on a train will be scrolling through their phones, completely unaware of the machines buried beneath their feet that made the whole thing possible. If this video changed how you think about what is happening under the ocean right now, hit like and subscribe for more. Turn on notifications so you never miss a video. And I want to hear from you. These machines spend months digging through the earth, and when they finish, they are sealed inside forever. If you could build an undersea tunnel anywhere in the world, where would you connect? Drop your answer in the comments.